Hello and welcome to lesson 5.3, derivatives of exponential functions. Today we're going to recall some skills with the derivative of exponential functions and apply that to every exponential function out there. So first of all, recall that if you have the function f of x equals e to the x, well, the derivative of that is just e to the x. Now, if we extend this using chain rule, meaning that if our exponent is something like a function, then what we can do is we can again apply chain rule, which means the derivative of the outside function is just e to the h of x, and then we multiply it by the derivative of the inside function, which in this case is just h of x. So multiply by h prime of x. And there you get the derivative of your exponential function if your exponent is something other than just x. So continuing on, we're going to continue to expand this. Now to find the derivative of any function to the exponent b to the x, where b is a number greater than 0 but not equal to 1, we're going to use first principles. So remember that derivatives by first principles, so in other words f prime of x, is calculated using the limit as h approaches 0 of f of x plus h minus f of x over h. So what we're going to do is we're going to extend this and expand. So now I substitute x plus h into the expression, and I also substitute x into the expression, and come up with this expression that we have right here. Now please remember, if you have something like b to the x, and you multiply it by b to the h, that's equal to b to the x plus h, because you can add the exponents because the bases are the same. So we can continue with this expansion in this format. Okay, so now that we have that, what we can do then is factor b to the x out of this expression. Now, because the x does not pertain to the value of h, you can actually put it outside the entire function and multiply by the limit as h approaches 0 of b to the h minus the value of 1 all over h. Well, this is where it gets a little tricky. Now we need to find out what this limit actually works out to be. But the thing is, you realize that you've already seen this before, that this limit as h approaches 0 of b to the h minus 1 over h is going to be some constant, and the b to the x, or the a to the x, whatever you wanted to call it, is going to remain outside the expression. So in order to solve this, I'm going to borrow some ideas that I know about exponential and natural logarithms. Okay? So first of all, please realize that the expression b is equivalent to e to the exponent ln of b. If you realize that, well, what you can do is you can actually expand this by expressing both sides by raising it to the exponent of x, like so. So, what this now gives us is b to the x is equal to e times, to the exponent ln b times x. Well, what I can do is actually find the derivative of both sides of this expression. So I'm going to throw a derivative on both sides of this expression. because if these two expressions are equal, then the derivatives of these things also will be equal. Well, we just found on the previous page that the derivative of b to the x is b to the x times the limit as h approaches 0 of b to the h minus 1 all over h. On our first page, well, we found out the derivative of any exponential function that's based on a natural exponential function. Well, that's just e to the ln of b times x times the derivative of the exponent. Well, the derivative of the exponent is just going to be ln of b. Now, because the b to the x and the e to the ln b of x is the same, therefore what we can conclude is the limit as h approaches 0 of b to the h minus 1, sorry, I wrote that wrong, all over h is equal to the natural logarithm of b. That means if f of x is equal to b to the x, then the derivative of such a thing is just b to the x times the natural logarithm of whatever the base is. And you'll see if the value, if that base was e, this is going to cancel out because ln e turns out to be 1. So now we can find the derivative of any exponential function with any base. Okay, so let's apply this. So we're going to calculate the derivative, which means differentiate all these different types of functions right here. So the derivative of y equals 5 to the x. Now that's just y equals 5 to the x times the natural logarithm of 5. Because the 5 is something other than e. Let's try f of x equals 4 times e to the x now. Its derivative is just 4. Derivative of e to the x is just e to the x. So that remains the same. Let's try the next one. G of x. So if g of x is equal to 2 times e to the negative x, because 2 is a constant, again, the derivative of this is just 2. Leave the 2 alone. Derivative of e to the x is e to the negative x. But because the exponent, in this case, is a negative x, you have to multiply by the derivative of the exponent, which is just negative 1. So simplify this, you get negative 2e to the negative 2x. Okay, this next one's a little bit more complex. So h of x is 2, which is a constant, multiplied by 3 to the exponent 2x. So leave the 2 alone, that's the constant. The derivative of 3 to the exponent 2x is 3 to the exponent 2x times the natural logarithm of 3, because the base is 3, times the derivative of the exponent, which is 2. And usually what they want to do, or what they usually do, is place constants in the front of the exponential function. So 2 times 2 is 4. I'll also put the ln 3 beside it, because that is a constant as well. And then they'll place the 3 to the exponent 2x here. Now sometimes you will also see that they'll write, instead of 3 to the exponent 2x, they'll write 9 to the x. But it's preferable to use smaller bases if you possibly can. And there's the derivative of that expression. Okay, let's try the next one. So here what we're going to do is we're going to calculate f of x, or given f of x equals 2 to the x, we're going to calculate the derivative of this thing. So that's just 2 to the x, since the base is different, multiplied by ln 2. Now to calculate the slope of the tangent at the value when x equals 1, all you have to do is substitute 1 in for x. So 2 ln 2. Please realize you could write this as ln of 2 squared, or ln 4, but again, most times what they're going to want to do is they're going to want you to get to the lowest base, or lowest argument possible. So if you can rearrange it or change it into a something with a smaller base, like the 4 can be expressed as 2 squared, you're going to want to do that and then rearrange it and change it into 2 ln 2. So that turns out to be the slope of the tangent. Okay, last problem. Okay, so if f of x is equal to 3 to the x, calculate f prime of x. So again, f prime of x in this case would be 3 to the exponent x times the natural logarithm of 3. So part B asks us, how does the graph of the derivative compare to the graph of the original function? Well, the original function was 3 to the exponent x. The derivative, as you can see above, is 3 to the x times ln 3. So that means the graph of the derivative is a vertical, because it's being multiplied right here to the function. It's a multiplication. Now calculate ln 3 on your calculator. What you'll find out is ln 3 turns out to be approximately 1.0986. Just going to round to 4 decimal places here. So as you can see, the number is bigger than 1, so it's a vertical stretch. Of the original. And that's how they compare to each other. And that answers that question, and thus concludes this lesson.